Hello, this is Dr. Stephen Bartlett, and today we're going to be covering Chapter 4B in my lecture notes, discussing shear stress, strain, and shearing. And the reading assignment for this lecture is sections 4.4 through 4.8 in Salgado. There's no other materials required, and then your homework assignment here is given from problems from Chapter 4. So let's get into the lecture. Similar to the way we talked about Mohr circles of stress, we can also develop some ideas about strain and then also define some more circles of strain. So to do so, first we need to talk about normal strain. So in this figure we can see that the coordinate system is x1 going horizontal and x3 going vertical. And if we look along the x1 direction, we can have some strain in the normal direction. Remember again, the x1 plane would be up and down vertical here. So we're talking about strains that are normal to that plane. And for the x1 direction then, we'll define a change in displacement going from B to B primed, where in this case there's elongation happening in that direction. So we'll call that du1, meaning the change in position with respect to x1, and then the original length we could call it just dx. So this is an incremental definition, meaning that we can now define the strain, the normal shear strain increment epsilon II is equal to the change in position with respect to that direction, dui, divided by the original length of that dx1. So what's important to notice here also is that we're going to define this negative in the case of elongation and positive in the case of compression. So this is consistent with what we did with Mohr circles of stress, where we defined compressive stresses as positive and elongation or tensile stresses as negative. So then the normal strain increment then is just a minus dui dx for this particular case. Okay, it's important to note for this particular shear strain theory that we're using out of Salgado, we're using what's called infinitesimal strain theory, which means we have very small strain increments. So in this type of theory, or small strain theory, the displacements and rotations are very small. In this case, we're really the undeformed and deformed configurations can be identical, meaning that the strains are quite small. We will find that in this case then the rotations can be expressed in terms of changes within the shear strain directions, and also the normal strains can be defined as changes in the normal direction. There is larger strain theory that is sometimes also used in mechanics, but we won't deal with it in this particular course. However, I teach another course in soil dynamics and also numerical modeling of soils, where we actually incorporate large strain theory. Okay, so we've defined normal strains. Let's look at how to define a shear strain. Here we see a square element that has undergone both some angular rotation or squishing of it, and then also we see it's being elongated too. So the movement of C is from C to C primed and B is to B primed. Of course, A is remaining in the same place. So now we can look at changes in the shear strains. So angle A1 is a shear or distortion angle, alpha 3, is a shear distortion angle also. And then gamma 1,3 is the shear strain of the x1, x3 plane. Notice this is the x1, x3 plane because we have x3 and x1 shown in the coordinate system. So we'll define why this is negative in just a minute, but if we're going to say that the changes in these angles equal to the shear strain. So gamma 1,3, which is the shear strain in the 1,3 plane, is equal to alpha 1 plus alpha 3. Or another way of thinking this is that the gamma 1,3 is approximately equal to the tangent of alpha 1 plus tangent of alpha 3. These two are approximately equal, alpha 1 plus alpha 3 and the tangent of alpha 1 plus tangent for alpha 3 for very small shear strains, because the tangent of alpha is approximately equal to alpha for very small angles. Thus we can represent the shear strain increment as the shear strain is equal to du. This is the change in position, du d3, the change in position in the x3 coordinate direction, this direction here, divided by dx1, which is the original length in this direction, plus du1, which is the change in position in this direction here, divided by dx3. Note we're using partial derivatives here because we're exploring changes in two coordinate directions, so thus we must use partial derivatives to express the changes in those directions. So the shear strain is defined in mechanics. Epsilon ij is based on small strain theory where incremental strains are used. The shear strain for this case is 1/2 of the engineering strain, gamma 1,3. So the small strain theory from mechanics, the incremental shear strain is 1/2 that of the gamma value that we defined up here. And it is essentially this equation here that we see divided by 2. So just keep that in mind if we're talking about small strain theory, and the mechanical shear strain is 50% of the engineering shear strain. This is a diagram developed by Dr. Lawton. I'll zoom out a little bit here, and we can see that we have a original square here that has been both elongated and undergone shear strain. So if we look at all these dimensions, first we should talk about the x1 direction being horizontal, the x3 direction being vertical. The plane, this plane down here becomes x3 plane because it is normal to the x3 axis. This plane here becomes I should say plane pi 1, 1, which is normal to the x1 axis, and plane pi 3, 3, which is normal to the x3 axis. Also then we can see that changes in the x1 direction are du 1 epsilon, changes in the y dimension are du 3 epsilon. Okay, and then those are along the strains parallel with those axes. Then we can also see there are some displacements that are not parallel to the axis. du3, that's gamma, and then we have the also displacement that's let's see, this displacement that has gone, this one here that's gone causing this distortion here is du1 gamma. So if you need to understand these relative displacements and things that are found in this in the equations, then you need to refer to this diagram. I will enlarge it just slightly here so that you can see again the original dx1, dx3, displacements in the normal directions here and here, and then displacements that would cause distortion or shear, du3 gamma here and du1 gamma. So just keep this in mind whenever you look at this diagram. Also, stresses are represented here. So Gatto, instead of using sigma, let's see, this would be, if it's we would call this sigma xx or sigma x in our previous discussion. It's now labeled sigma 11, and also sigma y or sigma yy would be this direction. And the shear stresses, he's used sigma also in his notation, where previously we used tau. So this would be, to us, this would be tau acting on the x-plane in the y direction. So this is tau xy, and this would be tau yx in the previous discussion that we had in the previous chapter. Okay, let's see if I can get this zoom properly. I guess it's the best I can do. So we can plot more circles of strain. This particular diagram is just a simplification of the one that we saw in the previous slide. So we have normal stresses here and shear stresses acting on this particular plane, and we can also express the normal strains and the shear strains here. Okay. Looking at these equations, I'm not sure if there's, I think there might need to be a negative here, value here, but I'm not sure. Let me look at the previous diagram. Yeah, there's a negative that's been dropped. So I will fix that here. Okay, so let's see how we define what is positive and negative shear strain. So if we focus maybe on this diagram here, and if we look at maybe the strains that are happening on these two planes, the normal strains and shear strains, if those shear strains cause the angle there to open up, or the L to become increased, then that is positive. Over here, if we look at this plane and this plane, there's a closure of that original L where it's collapsing. That would be defined as negative by the conventions that we need to adopt. So let's see, we need to understand that in this particular diagram, the red is the original shape. There is some elongation that has happened, stretching, but then there's also some distortion or angular change that's given the final configuration in blue. So taking these definitions, we can plot a Mohr circle of shear strain. And in this case, we have the normal strains, dE, plotted on the x-axis, and the 1/2 of the engineering strain, or what could also be the mechanical strain, because remember the mechanical strain is 1/2 of the engineering strain plotted on the y-axis. Okay, and so for a particular case then, if we know a normal strain and no shear strain acting on it, so that would be a principal strain, principal normal strain, we can plot that plot. And then if we know the corresponding minor principal strain, we can plot that point and we can draw a circle which represents the Mohr circle. So this coordinate is DE1, which is the normal strain in the x1 direction, DE3, which would be the minor principal strain in the x3 direction. Okay, the highest points on this circle would represent the place where we're at the maximum shear strain. In this case, the maximum shear increment divided by 2. That would be the maximum engineering. Let's put that in. Okay, just like we used the pull method before in determining the orientations and magnitudes of stress, we can use the same method to define the magnitudes and orientations of the planes of shear on Mohr circle strain. So let's just take a shot at this. Here we have a element that's originally gray, and we see it's been elongated. So we're going to plot that here on this axis. That is the principal strain. I've got this backwards. Yes, it's been elongated in the y direction, or the x3 direction, so it's been compressed in the x1 direction, so it would be plotting as a positive strain. And so we could look at this change in the, let's see if I can zoom in on this a little bit, change in this x direction with which has been shortened, divided by the original x direction. That would be that normal strain, and we would plot that point. Also, if we look at the x3 direction, then we see that it's been elongated, and so we would take the change, which would be the difference between here and here, divided by the original length, and that will be negative because elongations in the normal direction is plotted as negative, so it would plot here, and then we connect these 2 points. Now, notice this diagram here has no angular distortion. There's not any changes in the angles, so it's solely a compression in one direction and elongation in the other direction. So that's why these are principal strains, because there's no really shear strain occurring. So these both plot on where the shear strain would be 0. Okay, so to use the pull method let's pick any plane. Let's pick maybe this, let's pick this plane here. So by definition, that is the, let's go back to our diagram. So it's the pi 3,3 plane. Okay. And the elongation of that line due to the along that of that normal strain, which is acting on this horizontal plane, is expressed here. So again, like we used Mohr circles of stress, we need to find a strain on an old plane. So this is the strain on this horizontal plane. So we draw a line parallel to that plane till we intersect the Mohr circle of strain, and where we do that would become the pole. And then from the pole we can draw other lines. These show the planes, and if we drew a line up to here and a line down to here, then we would define these planes, and then we can get the normal strain and shear strain on that plane by reading the coordinates off of the Mohr circle. Okay. So let's just look at the left and rightmost points of the circle correspond to the magnitude of the principal normal strains d epsilon 1 and 0 and d epsilon 3 and 0. The highest point on the circle corresponds to the magnitude of the maximum engineering strain increment divided by 2, or that could be said as equal to the mechanical shear strain increment. Okay. Let's look at this once more, maybe in terms of what we might do if we were using the other plane. So this plane here is a vertical plane, and the normal shear increment to that plane is d epsilon 3, so we would plot that value. Since that's a vertical plane, we can't really move along the Mohr circle of strain in any direction, so by definition we're at the pole also, and we then could draw these same planes in here and get the same value. So what I want to point out is, just like the Mohr circle of stress, when we use Mohr circles of strain, the pole method is unique, and the pole is uniquely found from either of the planes that we start from. Okay, I also included a shear strain solver. This uses different sign conventions, but you can certainly go ahead and look at it. I popped into it here. This is a definition of a problem here. We have the normal strain on the pi 3 normal strain equal to 0.0206 in compression. We have 0.0406 in elongation, and the shear strains are equal to this. So let's go ahead and maybe plot this. So looking at this value here, it should be about 0.02, and we can see that here's 0.1, 0.2, so this is 0.206, which plots as the x coordinate, so that's the strain epsilon 1, strain epsilon 3, which is the shear strain, is about 0.0257. So that's where there's 2, 2.5, it's almost 2.6, 2.57, somewhere in there. Okay, so that's one point, and correspondingly we need D311, D epsilon 33 and D epsilon 31. So if we go back here, we see D epsilon 33 is 0.046 and the same 0.0257 that we saw before. So we can go down and check that. So this is over 1, 2, 3, 4 something, and this is down 0.20257, whatever the value was. So now we can connect these two with a diameter and swing a circle, and we have the Mohr circle of strain. Okay, then to get the coordinates of the major principal strain, that plane, pi 1 plane, we have to find the pole. So first we'll use this point here, and that plane, the strain represented on that plane was a vertical plane. So we draw a line parallel to that plane till we have the pole. Then if we draw a line up to where we intersect d epsilon where the shear strain 0, we have the major principal strain at 0.03 something. And then if we draw another line from the pole over to here, we have the pi 3 plane. I apologize, I forgot to put label these properly. So the pi 1 plane. And then pi 3 plane, and we can get what is the minor principal strain at about minus 0.05. So to check this, I went in and used the wheat link that I showed you previously, and I put in the normal strain. I put in this particular solver, compression needs to be negative and tension needs to be positive, and shear is positive by the right hand rule. And so this gives me the solutions that saying that the normal strain, maximum normal strain is 0.05 and the minor is 0.03, which what we got from the circle, other than we have to reverse the signs here because of our notation of this being positive and this being negative. Okay, so that is a simple example of using the Mohr circles of strain. So if you want to know the equations for this, this is coming from Salgado, and you can come in and calculate these for any plane that you want, and also you can calculate the orientation of the major principal strain. You can also find the principal strain increments from these equations. And just down here reminds you again that if we draw a diagram and we distort it where we're focusing maybe on this couplet in this area here, then if that angle opens up, then the shear strain is defined as positive. The next discussion we want to have using these Mohr circles of shear strain is where the potential slip surface may develop. So in this particular case, it's working the same example that we saw before, where we're causing some elongation in the vertical direction, some compression in the horizontal direction, and we constructed this Mohr circle of strain that we showed on the previous page. So the question we might have is, where does the failure surfaces begin to develop in this particular specimen? And they are predicted here by these kind of orange lines. There's a conjugate pair here. We don't know exactly which one of these would develop. Theoretically, they would both develop at the same time. In reality, though, maybe one in something that's not perfectly homogeneous, one might start to develop before the other. But these are the potential slip surfaces, and we can get their orientation from the Mohr circle of strain. So the let's work through this. Let's first find the definition about where do these occur. Let me zoom out just a touch here. And these potential slip surfaces occur on what's called these zero extension lines. and these are inclined an angle of plus or minus 45 minus psi divided by 2 from the plane where the minor normal principal strain increment d epsilon 3 acts. So this is the minor principal strain increment d epsilon 3, and the plane upon which it acts, I'm reminding you, is a vertical plane. So the normal strains are occurring in, in this direction up and down, but the plane upon which this act is this plane here. So knowing that that is that point there, to use the pole method, we draw a line perpendicular to that, parallel to that plane in real space, and we find out that we are at the pole. It looks like this is changed just a little bit. Just to remind you that that's at the pole. And so to find these planes, we must go 45 plus or minus psi divided by 2. So this psi represents the dilation angle. We'll spend a couple slides that are coming up next on how to determine that. But if you notice from our previous examples here, let me get back to the original definitions. That's still not it. This one. We notice this dilation angle here, psi. There's two ways of getting it. It's the angle from the center of the Mohr circular strain up to where the shear strain is 0 in either direction, and it is that way. It would be measured from some angle away from the vertical. Or if we take this coordinate here where the shear strains are 0, remember on this axis the shear strains are 0, and project that this direction, and this is also psi angle here. And I guess the important part is that this angle here and this angle here would be a right angle. So I guess you're coming through the point of tangency right through there down to here. So that would give you psi, which is the dilation angle, which we'll describe in just a minute. So if we go 45 plus or minus 45 degrees, so if we go minus 45, we're going in the clockwise direction, minus psi divided by 2, we would stop right here on this plane. Or if we come the other direction from the pole to plus 45 minus psi divided by 2, we'd come up to this plane. And so these red lines here show the 0 extension line or the orientations of these slip planes, and this happens to be 104.5 degrees inclination. I guess that would be measured around this direction here. Let's see what we know would be measured from the horizontal here over to there. So it's measured from here over to there. Okay, so that's how to determine those potential slip planes. Those are important to us because that's where the failure planes in the specimen would be predicted by theory. Now let's define how do we get dilatancy. First, let's just think of something undergoing pure shear strain. So I've drawn an element here in red, and I've distorted it by pushing it to the right. But notice that there's no expansion or contraction going on. So this is what we call pure shear. And in this case, there's no dilatancy or change in the volume of this specimen because the amount of area that we've pushed it to the right here and it's deformed here, those two triangles are equivalent. So there's no change in area, which I think you can just see. However, sometimes as we try to shear something, the area of shear may change due to expansion or contraction of the material. So in this case, we see that there is some dilatancy during shear, because as we've pushed it, we've also caused some change in area, represented by this blue line being above the red line. So if we look at just that simple geometry there in comparing, simple shear, pure simple shear against something that's shearing and dilating, then we can define the dilatancy angle here as just the angle from the corner of the undeformed square to the deformed square here. If we just draw that, that becomes the dilatancy angle. That's the geometric interpretation to it. So that angle, if we look at just the definitions from geometry, is just OZ divided by the absolute value OA. Let's see if those were defined previously. So the sine of the psi, or the dilatancy angles, OZ divided by OA1. So sine would be of this angle would be side opposite over hypotenuse. Would be side opposite here over hypotenuse. And it can be estimated from the strains, as we see here. Or it can also be estimated from the maximum volumetric strain divided by the shear strain, though we have not defined volumetric strain yet, but I will do that in a minute. So that dilatancy angle becomes important to us, because it tells us how much things might be opening up or dilating, or the opposite could be that this upper line here drops down below here, suggesting that the specimen contracted as it was undergoing shear. So let's look at just volumetric strain. This is kind of where we have elongation going on in two directions but no shear. So we see we have to develop a three-dimensional nomenclature. So x1 axis is out of the page, x2 axis horizontal in the page, x3 axis is vertical within the page. And we have corresponding incremental strains, DE2 here correspond to horizontal, DE3 correspond to the vertical, so this is the same as we did in 2 dimensions. Now we have to add this DE1 along the x1 axis. So the change in the unit volume, the change in volume, we have to get what the volume is of the deformed shapes, so we can see that from this part of the equation. The 1, which is the original length, plus some du1, which is change in position in the 1x direction, this direction, plus we have another change in direction in du2 direction, which is that direction, and then we have some change in the d3 direction here. If we minus that by the original volume, then we have what is the change in volume, the incremental change. So the volumetric strain, dE, this V meaning volumetric strain, is the change in volume divided by 1. 1 is the original volume. And we make it negative to show that to make contraction as positive. In small strain theory, these DEV is very small. These second and third order terms, if we multiply this, we're going to get second and third order terms in this, we're just going to call those very small and neglect them. So we're just going to say the volumetric strain is just mainly due to changes in the DE1, which is the strain in the X1 direction, DE2, which is the strain, normal strain in the X2 direction, and DE3, DE epsilon 3, which is the strain in the X3 direction. So in terms of, we can just write this in terms of principal strains this way, as we've done before, referring back to our original nomenclature shown on this page. And we can have the definition of volumetric strain. Okay, so now let's define a modulus that you may not have come across before, which is called the Bolt modulus, which tells us what is the, if we take the change in pressure versus change of volume, then we can come up with a modulus. So we have some pressure here, which is causing some change in pressure and causing some change in volume. If we take the modulus then of that, then we just take the initial volume times the change in pressure causing some change in volume, and we can have the Bolt modulus. So the P is pressure, V is volume. The change in pressure with respect to volume is the partial derivative of the pressure respect to volume. This is the inverse of the Bolt modulus and gives the substance's compressibility. So this modulus then can be used that if we have some application of external pressure on some element, we can then use the Bolt modulus to predict the change in volume. So we've done this before with normal stresses and came up with Young's modulus, and shear stresses also to come up with, later we'll define the shear modulus, but remember the Bolt modulus deals with volumetric change caused by external pressures. Okay. So this is useful. Eventually we're going to get to a state where we want to express shear strain in a matrix formulation. So let's just look at this law, stress strain law. In this case it's going to be called Hooke's law for elastic homogeneous materials. So if we have some normal stresses x, y, and z, and some shear stresses tau x, y, and we have some shear strain components epsilon x, epsilon y, and gamma x, y, then we can express this in terms of Hooke's law, where the some changes of stress times some modulus or D matrix times the strains. So if we want to, solve for strains, then we can use Hooke's law and essentially say that the strains are equal to the stresses divided by the moduli, at least the moduli matrix. So E in this case is Young's modulus, or the elastic modulus. And let's look at the stresses. Stress in the x direction, stress in the y, tau x, y would be shear stresses. So this is a two-dimensional formulation times some material constants, in this case Young's modulus, and mu here is Poisson's ratio. And then we have this matrix here, expression Hooke's law, where we want to know the terms on the diagonals, and these two terms here are Poisson's law. These others are zero, and this would, these stresses are equal to this times this, or these strains are equal to this divided by this. Okay. So this D matrix, which combines the material properties and the appropriate matrix formulations for at least two dimensions, is shown here. What we mean by the plane strain case is all of the strains are occurring essentially in the XY plane. There's no there's nothing happening in the Z direction, so it's truly a two-dimensional case. And when we have elastic constants, if we know any two elastic constants, we can calculate the other constants. And so this table here shows you Young's modulus, how it's obtained. If you have, of course, the shear modulus K, bulk modulus and shear modulus G. We haven't defined shear modulus yet, but Poisson's ratio there, its formulation. There's shear modulus in terms of Young's constants, bulk modulus in terms of Young's modulus and Poisson's ratio, and the constrained modulus also. The constrained modulus and shear modulus haven't defined. I could write the simple versions of that. Let's just take a second to do that. That the shear strain gamma, I'm just going to write gamma. Well, the shear, let's go back to this Hooke's law and write it for shear strains. So tau, which is the shear strains, is equal to some, D matrix times the shear stresses. So that would be Hooke's law written for shear. And this D matrix then will show you later on for shear, but it will use the shear modulus. And then the constrained modulus. If we think about Young's modulus, you are taking something like this and you are allowing to maybe some kind of force to act upon it. Let's just draw it here in the vertical direction. But notice in this direction, it's unconfined, so it can deform in this direction. That would be for the case of just unconfined compression. However, if we take and confine this like we do in a consolidometer, where we put walls on both sides of this, constrain it in this direction, where then only deformation is allowed in this direction and none is allowed in this direction. So we've got it constrained on both sides, like we do in a consolidometer cell that we do in soils to do the consolidation testing. Then we don't get Young's modulus because it can't deform in this direction. So the modulus then we get in that case where we look at these vertical strains versus the amount of change in volume is the constrained modulus. So this is the definition of constrained modulus, and you can see that if we know Young's modulus and Poisson's ratio, then we can get it. Or if we know the bulk modulus and shear modulus, we can also calculate the constrained modulus. So I will go into some laboratory testing later on and just show you how to determine some of these things. So I've just taken and written Hooke's law here. I have Young's modulus and Poisson's ratio given to me, and so I formed a D matrix. I'm doing this for actually 3 dimensions. So I've got X dimension, Y dimension, Z direction, and those are the normal stresses. These are the shear stresses in the X, Y, Y, Z, and ZX directions. And I've taken those and put those in terms of the shear stress matrix. In this case, we've set all the shear to 0. So that means this state of stress really is a principal state of stress. The D matrix then for 3 dimensions becomes this. And so then solving this for matrix D, or the delta, becomes this. And then the shear strains, this, which is just the delta times the sigma. And we have the shear strains that we've gotten from solving this using the matrix operations. Okay, so that's a 3-dimensional application of Hooke's law. I don't know if you'd have to do 3. You would have to maybe do 2 sometimes. So this is the formulation that you'd be for 2-dimensional stresses. Okay. But quite often we have stresses and we have material properties and we want to know strains. So matrix-wise, you've got to divide. You've got to solve this algebraically. So the strains is equal to the D matrix divided by the stress matrix. Okay. Let's talk about some practical applications to all of this theory we've gone through. We're finally getting back into a real-world situation. Let's imagine first what we call at-rest earth pressure. So we have a simple situation here where we have the horizontal plane representing the ground, and we go some depth below the ground surface Z, and this material is defined as gamma. Again, excuse me, this is not shear strain now. This is the unit weight, cohesion, and friction angle. So these are material properties. Now, when we look at this at-rest condition, so this plane would go on infinitely. We'll find out we have some vertical stresses and some normal horizontal stresses. And in terms of what we've been talking about before, this lecture, change the size of this, the vertical stress we'll say is going to be larger in this particular case, so we'll call it sigma 1. The horizontal stress is sigma 3. There are no shear stresses acting on this. And we can write the ratio of defined horizontal stress. We can take K naught divided by K1, which is what's called the earth pressure coefficient at rest. So if you really look at this just algebraically, it probably would have been better just to call this over here that K naught is equal to the ratio of sigma H divided by sigma V. Let's change these back to get these out of symbol notation. So this earth pressure coefficient at rest, called K naught, is simply the ratio of the horizontal to vertical stress. Now if the vertical stress is larger, then K naught is going to be less than 1. Why do we need to know this? Well, if we know this K naught value, which we can predict maybe from other equations, then we can get this ratio of stresses. You've dealt a lot in this class with sigma V, and also sometimes sigma V primed. But now we want to know the horizontal stresses too, acting on the ground. to get this ratio of the horizontal to vertical stresses here, we can estimate it from the friction angle. Notice phi is the internal angle of friction. So for normally consolidated sediments, K naught here is simply the 1 minus the sine of the friction angle. Okay, if the sediments are over-consolidated in any manner, have an over-consolidation ratio, then we correct for that. So it's 1 minus the sine of phi times the OCR to the negative 1/2 power. Okay, and remember the OCR is the pre-consolidation stress in the vertical direction divided by what is the current effective vertical stress. So that's just kind of a refresher from GO1 if you've forgotten that equation. Right here. K naught also, if we know Poisson's ratio from elastic theory, can be expressed by this equation. It's Poisson's ratio divided by 1 minus Poisson's ratio. Now, quite often, we don't have an infinite soil mass, a horizontal plane of soil. We may have something like a retaining wall. And as this retaining wall begins to move away from the soil, we can cause failure planes. And these are the failure planes. Remember when we talked about the zero extension line, this is the same kind of concept, that these lines now will develop in the soil mass. And they occur at 45 plus phi divided by 2, where phi is the internal angle of friction. This case is due to where there's really no dilation or contraction going on. We just move the wall away and this soil mass tries to reach failure. So we will use this concept in retaining wall design to predict what is the failure planes, and from that we'll use free body diagrams also to determine what are the states of forces acting on the retaining wall. So for right now, if I ask what is the inclination of the planes that cause failure for a wall where the wall is moving away from the soil mass, going in extension, then it's 45 plus phi divided by 2 would predict that particular failure surface. The other case where we push the wall into the soil mass, causing it to compress, then these failure planes here form kind of in this subvertical direction, and they are predicted to be at 45 minus phi divided by 2. And we call that the passive case, where we're pushing the soil in and causing compression, or where we're causing extension and causing these at 45 plus phi divided by 2. That is the active case. Okay, I want to note that this theory is only for perfectly frictional materials or cohesionless materials where C equals 0. Otherwise, we'll have to change our theory. So let's look a little bit more about this active case using Mohr's diagrams. The active conditions shown here, this gray area represents, well, I guess it's not too gray on what you're seeing, but it's this area here is moving away from the soil mass in this direction. Okay, and reaching a failure state. So we know that that failure surface is going to be divided by phi, is represented by phi, the internal angle of friction. As we look down here, we initially start at some state of stress where we have sigma v, which is the vertical stress, and we have the horizontal stress, and we're just going to represent the horizontal stress. Remember, K is horizontal divided by vertical, so if we take K divided by K times vertical, then we have the horizontal. So at rest, we have the vertical stress here, the horizontal stress. But as this wall begins to move, we're relieving this horizontal stress, and so this envelope, this circle is getting larger in this direction until we reach a failure state where it touches this. So this would be the state of stress at failure. So we've replaced the K naught, which represents before failure, to Ka by the value which is at failure. So this is a Mohr circle diagram where we reach the active state by failure, by relieving the horizontal stresses. I think later on I'll probably talk about the triaxial device and how I can set up the triaxial device to mimic this particular failure condition. But again, just remember that the horizontal stresses are decreasing starting from this initial state of stress where K, this is sigma V1, this is sigma prime H, sigma prime V, sigma prime H, and we're now decreasing the stresses in the horizontal direction, reaching this failure state. So just watch these diagrams and notice which way we're moving and how these circles change. And we can predict that failure plane using the pull method. This is the plane upon which the minor principal stress acts. We draw a line parallel to that plane. We have the pull. If we draw a line up to that failure surface, that would define the failure plane, and we'll find out that it's up from the horizontal 45 plus v divided by 2. Okay? Up from the horizontal. So coming from up here. So this is just showing everything using essentially the trigonometry of how to get these constructions using our notation of sigma 1 is the principal major stress, sigma 3 prime is the minor principal stress, and the potential failure plane shown in here, and the states of stress both in the vertical and horizontal direction at failure, because notice we're using Ka, and so that means we've reached the failure state here. Okay, we can use these geometries simply to write the differences in the stress. This is the difference between the major and minor principal stress, or the diameter of this circle at failure, and we can write it in terms of this. And we can also then use just simple algebra to formulate it in many, many different ways. Probably the most useful out of this is K is 1 minus the sine of phi divided by 1 plus the sine of phi, or it's equal to the tangent squared of 45 minus phi divided by 2 to get Ka. So don't confuse Ka with K naught. K naught is where we hadn't reached failure and we have a perfectly horizontal plane and no wall that's moving. This is a case where we've reached failure, so this is different than calculating K naught. Let's review the passive case. So in this situation now, we're taking this initial wall element here and pushing it into the soil mass. So our initial state is here. This is the same as we started before, but now as we increase and push in the horizontal direction, we're increasing actually sigma 3, so it would eventually come to a point here and then start sigma 3 would be increasing this way until we reach this failure state by pushing the wall into the soil mass. I think you can intuitively understand that the soil is stronger when we try to push in against it in compression than pull away from it in extension. So this is the friction angle. It hasn't changed. It's still phi. It's the same as we had for the active case, but now we see the pressures are much higher in this direction as predicted by this particular theory. And so again, defining everything in terms of major and minor principal stresses, we can go ahead just like we did before and come up with what is the coefficient of passive earth pressure, K sub P is equal to 1 plus sine of phi over 1 minus sine of phi, or tangent squared of 45 plus phi divided by 2. So just look at this for passive earth pressure and compare it to active earth pressure. And you see it's 1 minus sine over 1 plus sine here, or it's 1 plus sine over 1 minus sine, and in here it's 45 plus phi divided by 2, or for the active case it was 45 minus phi divided by 2. So the signs are changing here. This is considerably smaller, the active pressures in this failure mode. Maybe for a typical sand this might be about 0.3, where this value here might be as high as 3. So let's stop. I'll continue on in just a moment, and we'll talk about the active and passive states and compare them in Mohr circle space. So let's spend a minute talking about these Mohr circles that we've just looked at. The upper diagram here shows 2 Mohr circles. The first one for the active case. So in this case, the sigma h is decreasing as we pull the wall away from the soil mass until we reach a failure state here when we touch the Mohr circle, which is sigma h is equal to sigma 3. And this other diagram here shows a passive case where we're pushing the soil wall into the soil mass. So the horizontal stresses are increasing until eventually we reach where sigma h at failure is reached here once we touch this Mohr failure envelope. So notice that the horizontal pressures to bring it to failure by pushing into the soil mass are much, much greater than they are when we pull away. This next diagram below that I'm going to show you, let me zoom back out here. Let's maybe go just a little more. Is the same as the above diagram, but instead of using sigma 1 and sigma 3, we're using sigma vertical for the vertical stress and sigma h for the horizontal stress, and where appropriate, the appropriate Kp value, which is the passive resistance coefficient Kp, and the active case would be using Ka. So you can review these two. These concepts we'll revisit when we get to retaining wall design. Next, let's just talk about the direct shear. I've talked already a little bit about this in class and how the direct shear is done. If you'd like to watch a video, I've included a link here for you that you can go in and look at that test. And just some advantages of the direct shear test is it's inexpensive, it's relatively fast, it's a simple test, and it's good for determining sliding resistance along horizontal planes. However, there are some major disadvantages. It's really generally used for drain conditions, meaning granular soils. If we use it for cohesive soils, then we have to shear quite slowly. The shear plane, which is a horizontal plane, may not be necessarily the weakest plane within the specimen, as we've kind of learned. And there are stress concentrations that occur along the edges of the box at the sample boundaries. And the principal stresses, the major and minor principal stresses, rotate as the shear test proceeds. So just to give you an analogy for this direct shear, I think the easiest thing to do is go back to your physics where you learned about a sliding block. So there's a block placed on a plane. It's held in place by friction. And then eventually we raise it up to a particular critical theta angle where then the block initiates sliding. So just to kind of do a free body diagram, we can say the forces resisting sliding is a normal force acting, in this direction. Times the coefficient of friction mu. So I've drawn this as the free body diagram at the centroid of the block. So in this case, N is acting this way. The sliding force, which is Fs, is equal to mu times N, acts in this direction, and of course there's the weight of gravity acting downward. So as this angle theta increases, this sliding force increases, and this normal stress or normal force decreases. So writing equations of equilibrium from statics in the y direction, the normal stress minus the weight of the block times the cosine of theta, which is the inclined angle, must be equal to 0. So the normal stress is just W times cosine theta. In the direct x direction, then we have the sliding force resisting sliding, and we have W minus sine theta, and that must be equal to 0. So the sliding force then becomes W times sine of theta. If we substitute in for the sliding force mu times N and then solve for mu, then we get mu, which is the coefficient of friction, interface friction between the two planes, would be W divided by N times sine theta. And W over N is the hypotenuse divided by the side adjacent, which is 1 over the cosine of theta. So mu can be written as the sine of theta over cosine theta, or just simply mu is equal to the tangent of theta. So let me just go back to the free body diagram and explain what that means. Now, as we increase this angle, we reach equilibrium when the sliding force as the sliding resistance mu times N is equal to the gravitational force acting from W in this direction. So when we're at equilibrium and this begins to slide, then mu also is known as the tangent of mu is also known as the tangent of the interface friction between these two materials. So kind of with that same analogy, we'll look at a direct shear box. I've drawn the sand in the shear box using dots here, so that represents sand. Then they have the upper half of a rigid box, the lower half of a rigid box, which are metal. We have F acting in these directions, pulling in the horizontal direction, and we have a normal force acting downward. This normal force is applied by a weight similar to the consolidometer. There's a suspended arm here that pushes down on the box, just like we did in the consolidometer. We hang weights here to produce the normal force in the box. Okay, so initially we maybe start at a fairly low normal force, and we watch it shear. It might reach a peak and then start to decline somewhat, and we'll pick that peak as the peak shear force. We maybe allow another test where we increase the normal stress. So the normal stress for test number 2 is greater than number 1, and we repeat the test and we shear. It goes up to even a higher value and then begins to drop off, and we'll call that the peak force in number 2. And then we repeat it again for a normal stress 3, which is greater than normal stress number 2. So we're increasing the normal force, and we allow another peak to be determined. And so we're really interested in these peak forces and plotting them. So if we remember that shear stress is the peak force divided by the cross-sectional area of a shear, we can change these to shear stresses once we know F1, F2, and F3 in the cross-sectional area of shear, and we can plot them this way. Now instead of force, we have shear stress versus displacement. And often too we have a vertical dial gauge on the box, which I should mention, placed right in this area, so as if the sample goes up or down, dilates or contracts as we shear it, then we can measure that amount. This is what you should have done in class. You may have forgotten that aspect, but quite often we initially have some little bit of contraction. A negative change in height is a contraction, and then some expansion as the soil continues to shear and dilates a little bit. So we can plot those normal stresses at failure, and if we take a straight line down through zero, and meaning there's no cohesion intercept, then the slope of this failure envelope on a shear stress versus normal stress plot is the internal angle of friction. I think I've gone through this before, but we'll just do a quick review of how the angles rotate at failure. The principal stresses, as we start this test, the normal stress is the only stress applied, and there's zero horizontal stress. So we're really a Mohr circle that looks like this, coming from here to here. But as we increase and begin shear, eventually the normal stress keeps increasing, and then we reach a failure point. So I've redrawn this now that this is the sigma 1 at failure and sigma 3 at failure, the minor principal stress at failure, the normal principal stress at failure. Now let's see if we can use the pole method to determine the angles of these planes. So we'll define first sigma 3 here, and we know that it's acting on a horizontal plane. So we start here at state of stress is sigma 3, draw a line parallel to that horizontal plane, find the pole. Then if we draw a line down from the pole down to sigma 1 at failure, this line here, let me zoom in just a little bit, this line here defines the plane upon which the major principal stress acts. The major principal stress is perpendicular to that, so this is the direction of the major principal stress, and likewise this is the plane upon which the minor principal stress acts, and if we draw a line perpendicular to this, this is the direction of that stress. So we know now that the stresses have rotated. Initially the sigma 3 was horizontal, sigma 1 was vertical, and so this is what's happened, this stress rotation, and we can't really control this. This just happens during the test. Okay, the triaxial device, which you've briefly also seen in Geo 1 at the last lab, we have a ram or a press that can push downward and apply some additional force or stress to the top of the specimen. The specimen is contained here in the cell, the plexiglass cell. Remember in class I discussed that inside, let's see if I can even zoom more, that the specimen is a sample of soil inside this, and there's O-rings top and bottom and tubes that go into that so that we can control the pore pressures and water in and out of the specimen independent of the cell. So we can apply a increase in vertical stress. We sometimes call that the deviatoric stress in this direction. In the horizontal direction, or in all directions within this cell, we can also increase the confinement by placing water in here and pressurizing the water, and we can pressurize that through here. These pumps here control flow in and out of the specimen. This one here is hooked to the outer cell, so we can control the pressure to the outer cell, which is the plexiglass cell, and then this one here is connected to the valves, which are connected to the inner cell, so we could control the pressures or flow in and out of the inner cell. So in theory this is a much more attractive test, because we can then control the major and minor principal stresses and let failure occur in the specimen however it so chooses to do, without forcing it in a horizontal plane. So this is just kind of the drawings of the inner cell and how water goes in and out. These pumps are highly accurate. They can measure pressures quite accurately, and also any flow in and out of the either inner or outer cell. So let's just talk about, different types of tests. These are triaxial tests. We can break them into three major categories: consolidated drained, consolidated undrained, and unconsolidated undrained. So let me maybe go back to the picture of the test device and explain to you what's happening in each of these tests. So in a consolidated drain test, we'd have the specimen in here and we would flow water in it until it's completely saturated. And then we would begin to consolidate it by applying pressure to the cell, but not putting any pressure in the vertical direction downward. So it has a state of stress where it's pushing it inward in all directions by the water. And we would allow it to consolidate. And during the consolidation phase, we would have to open up the drain valves on the specimen itself, which are these valves down here, and allow water to flow into the pump and measure how much water is produced, and that will give us an idea of the volumetric change of the specimen. So the important thing is we're consolidating it first with the drain valves open and allowing the specimen, any water that's in it, to move inward into the pumps as it consolidates. Okay, and then to complete a consolidated drain test, then we would leave this valve open to the specimen so that water can dissipate as we shear, and we apply a vertical stress. Again, the deviatoric stress, we start pushing downward on the specimen and then causing it to compress, and then measuring the force versus displacement and trying to find what is the peak force and resistance. Quite often, like we saw in the direct shear test, this will pick up a considerable force and then eventually it will reach a peak and then drop off. So that describes a consolidated drain test. In consolidated undrained test, we repeat the consolidation phase. So this is a new specimen we have in here. We're going to do a consolidated undrained test. And in this case, to do the consolidation phase, again, we're not applying any vertical force down here. We've just added pressure to the cell here, and we're pushing inward in all directions. So sigma 1 equals sigma 2 equals sigma 3. It's an isotropic stress, and we allow it to consolidate by having this drain valve open and measuring any flow of water out of the specimen into the pumps. And then to do the undrained test, we shut the valve off out of the specimen so it can no longer drain, so that all water would be forced to stay within this membrane, and we start to shear it, but we have a pore pressure transducer so that we can measure what pressures build up in the cell, in the specimen, and that will give us an idea of what pressures might be. Generally, maybe as we shear, we might get positive pore pressures. So that's a consolidated undrained test. The last is an unconsolidated undrained test. Not used very often, but in this case we put a specimen in and we put water around it, but we don't pressurize the water at any. We just leave it maybe at or near atmospheric, so we're not causing any consolidation, additional consolidation. And then we essentially apply a deviatoric stress with the drain valve closed so pore pressures build up, and that becomes an unconsolidated undrained test. I will explain later on the uses of these tests for engineering analysis, but for right now I just want to give you the description again. So consolidated drained, so the consolidated phase, C means we're doing consolidation. In the shearing phase, when we apply the deviatoric stress, that's again the vertical stress acting downward by the piston. If we have the drain valve open to the specimen, then it's drained. If we close the drain valve to the specimen, then it's undrained. And then the unconsolidated undrained, we don't consolidate the specimen any, and we shear it undrained. Let's talk about at least the three different tests and the type of envelopes that we would expect, mainly from a hypothetical material. So for the consolidated drain test, here I've drawn the angle, and notice I primed this, meaning that we call it sometimes the drain friction angle or the effective stress friction angle, meaning that we have allowed pore pressures to dissipate because it's a drain test. And eventually we'll reach a Mohr circle that looks like this and can draw an appropriate drain friction angle using this line right here. Okay, in the undrained test, we do consolidate it, but then we close the drain valve as we apply the deviatoric stress from the piston. We're going to build up pore pressures. So this difference here between these two values here at failure is the amount of pore pressures that were generated at failure in the specimen, and the Mohr circle shifts this way, and the undrained failure envelope actually is below the drain failure envelope. So this tells us that soils are stronger when the pore pressures can dissipate. When they can't dissipate, then they have a lower friction angle. And notice this is not primed, meaning that this test was done undrained. Okay, so that's how we can kind of interpret that from the Mohr circles at failure. The unconsolidated undrained test basically says no matter what we do, when we shear it, we generate pore pressures and we get an envelope that's essentially horizontal, so the friction angle is 0, and this intercept here would be kind of a fictitious cohesion. So this really is not that useful because we don't very often shear soils unconsolidated and undrained. So sometimes another name for the unconsolidated undrained test or UU test is sometimes called useless and unreliable. I don't really like this test at all, but I just pointed out to you that if you hear the terminology, you'll know what it is. So lastly, let's just look at kind of the ways we can come to failure in the triaxial device. The first one is axial compression. So we start with, initial state where sigma 1 is equal to sigma 3. We apply an axial stress and consolidate to this state here. And then we continue to increase the deviatoric stress in compression in the axial direction, which means the vertical direction, until we bring it to failure. Once we've reached the peak stress at failure, then we can connect a line going through 0, because we're going to be, again, this is only valid for sands or cohesionless material, sands and gravels. Then we can draw a line up through here and get the friction angle, phi. So this model is similar to what would happen when we take a foundation and put some type of vertical element like a column or wall and placing load on it. So this is quite a common loading situation. Another way we can bring it to failure, though, is called lateral extension. So for this case, we might consolidate to this situation where we have sigma 1 still greater than sigma 3. And then we start decreasing sigma 3, which is the cell pressure. And so as we start decreasing the cell pressure, our Mohr circle grows and grows, and sigma 3 is diminishing until we touch the same failure envelope, but at a much lower peak. Notice here's the peak here, and here's the peak here. It's lower. So this models some case where maybe a retaining wall might be moving away from a soil mass. This is the lateral extension mode. So this would be the proper test if we wanted to get what is the right failure envelopes for a retaining wall moving away from the soil mass. Okay, let's continue on. There's 4 ways that we can bring a specimen to failure in the triaxial device. The other is essentially called axial extension. So we start this test again with sigma 1, the vertical stress, greater than the horizontal stress, the confining stress, and consolidate here. But now we start pulling the vertical stress away, so we're actually pulling on the specimen in extension. That's why it's called axial extension. So eventually the Mohr circles come to here, and then eventually what was the vertical stress becomes less than the horizontal stress, and we keep drawing forward more circles, and then eventually we reach the failure surface down here. which defines the Mohr circle at failure. Okay, so that would model unloading. So maybe we have something buried and we're removing by excavation the vertical stress by removing soil, and we might be able to bring the soil to a failure in this horizontal extension mode. So we'll talk about this case too later on in design. Let's see, I forgot one here. The last one is lateral compression. So again, we start with the vertical stress greater than the horizontal stress, which is generally what happens in the ground. And then we push into the specimen. We're increasing the cell pressure. So the cell pressure is increasing. It begins equal to sigma 1, and then it eventually becomes greater than sigma 1. And we touch the failure plane down here at that phi, which is the same phi as that, and we reach a failure state. So this models the case where we might be pushing a retaining wall into the soil mass, which is the passive case, as which we'll talk about later on when we get into retaining wall design. One way of plotting these is, instead of plotting the circles themselves, is you can just plot the top of the circle. These are known as S-T plots, ST plots. So ST is the center of the, S is the center of the circle, T is the top of the circle, so we're plotting those coordinates. And if we look at those coordinates, we can tell which failure mode we're trying to induce from the test by the direction that these go as we increase or decrease this or change the stresses. So if it goes up and to the right, that's axial compression. If it goes down and to the left, that's lateral compression. If it goes down and to the right, if it goes down and to the left, that's axial extension. If it goes up and to the left, then that's lateral extension. So this is the same. We're just plotting again the tops of the Mohr circles on these T versus S plots. So it's just a change of our reference coordinates. And also, Salgado talks about PQ plots in maybe 2 and 3 dimensions, and I've given you the same terminology in PQ plots, where Q is 1/2. Something seems wrong in this. That half should be there. I better be careful. I'll check this equation. I don't think this one's right. Anyway, we can plot in PQ space, and here's P described, which is just the mean principal stresses, sigma 1, sigma 2 plus sigma 3 divided by 3, where this is the deviatoric stress is squared, take the square root of it. And I think we just times it by 1/2, but I'll check that for you and fix that in my notes. And so we can plot this also. These angles here are no longer phi. If we plot them in this type of PQ space, they become psi, which is the slope of the Mohr's Coulomb envelope, and in PQ space, but sine of phi, which is the internal friction of angle, which is the slope in sigma tau space, is equal to the tangent of psi in PQ space. Okay, well, I think that's all the theory we need. We'll probably have to revisit this a little bit, as we progress this semester, as we talk about some of these failure modes and talk about how the soil is brought to failure and what is the proper, friction angle or cohesion to be using. But this, kind of concludes the theoretical part of this course. From here on out, I think we'll be talking about more practical design issues.